So phone's away. We're red light. We talked about Newton's laws of motion. One, law of inertia. Something's in motion, it's going to stay in motion until an unbalanced force acts upon it. If it's something that's standing still, it will stay still until, again, an unbalanced force acts upon it. Second law, force equals mass times acceleration. Third law, all forces happen in pairs. There's an equal and opposite reaction. So force and mass. Force is a push or a pull that is required to change an object's motion. A vector shows magnitude and direction. That's a review for you guys. Okay, and there are 4 known forces in the universe. Electromagnetic, which is caused from electrical and magnetic interactions. Strong nuclear, which is responsible for holding the nucleus together in the atom. It is the strongest force, and because it acts over the shortest amount of distance. Gravitational is the weakest force because it acts over the longest distance. And then you have weak nuclear, which is responsible for radioactivity and atoms. So if we were ranking them, if we're ranking the order of strength, this is 1, this is 2, this is 3, and this is 4. Okay, so you have strong nuclear as your strongest. Electromagnetic would be second. Third would be weak nuclear. And then fourth would be gravitational. So, and when we talk about categories of forces, the categories of forces are contact, which means you can actually touch it, or a field force, which means it's around you. Okay, you can't actually lay your hands on it, but you see what the results of being a field force are. All right, so the contact forces. Contact force exists when an object from the external world touches a system and exerts a force on it. So remember, I gave you this example the other day. My wallet. Don't even think about it. My wallet's sitting on the table, right? Are there any contact forces right now on it? What? Gravity is a field force. But if I move this, is there contact? Yeah, so I am applying, it's called applied force here. Okay? Again, I'm not doing anything. Okay, it's sitting there. I'm applying force, it's moving. Okay? Again, not applying any force, it's not moving, it's staying still. All right, so you're exerting a contact force if you're actually touching it. Now, there was another contact force there. It's called what is called a normal force. It goes in opposite of a gravitational force. Okay? So the table itself or the desk itself was exerting a contact force. What are examples of contact force? Friction, applied, tension, and spring. Those are types of forces, of contact forces. Friction makes sense because friction is going to be rubbing against an object that's going across another object. Applied, you saw me, I actually touched the wallet to make it move. Tension, you can see the tension because it's hanging from the string. The string is contacting the object, and the spring, same deal. The spring is compressed. You can see that that's going to be a contact force. Field forces are objects that can move without directly touching something. So if I drop my wallet, why does it fall? It falls because of gravity. Gravity is a force, is a field force. You can't see it, but you can see the reaction or what happens with it. It will affect gravitational force as a field force. It affects the movement without being in physical contact with other things. The other field forces, magnetic, electrical, nuclear, again, all of these things you don't see, but they keep things together. And why is nuclear the strongest? Because it keeps together the nucleus of all objects, okay? It keeps together that of the atoms. The thing about it is that how hard is it to split an atom? It is so difficult. That's why that strength is so strong, but it's also so strong because it's over such a small area, so it can concentrate over that. So the third law of Newton says there are force pairs, okay? Usually normal and gravitational forces will be paired, okay? They'll go together. When an object's moving across something, the forces that will be paired are applied, the one that's moving it, whichever way it's moving, and friction, which is moving the opposite way, okay? It will also have normal and gravitational as well. And when an object is moving in the air, what do we know? What's always acting upon it? Got to be gravity, right? Gravity is always going to be acting upon it, and there's going to be friction. Air friction is going to be acting against it, okay? But remember, if something in the problem says free fall, what is not involved then? No, gravity's involved. No what? No air friction. Free fall means there's no air friction. All right. So mass is the measurement of how difficult it is to change an object's velocity. That's inertia. Inertia is the resistance to change in velocity. So mass is a measurement of an object's inertia. All right. So how do we represent these? We do it by drawing free body diagrams. Free body diagrams are a visual representation of forces acting on an object. It helps analyze the motion of the object, and they are absolutely essential for solving physics problems. Why do you think I was so obnoxious about making sure that you guys were drawing diagrams when we were doing 1D motion? Because you need to be able to see what is happening. I get it. I was being over the top about it. But when you draw it, it makes better sense. You're able to see it. All right? So why do we use the free body diagrams? It simplifies complex problems. Because you can just look at the object, you look at the length of the arrows, you can see which one has the most, and go from there. It clearly shows all of the forces that are acting upon the object. And it also allows you to make sure that you're following and applying the laws of Newton's motion correctly, not just effectively, correctly. All right. So when we ID forces, forces can be contact in nature, they can be field forces. We do not, when we're doing this, we do not at all. We don't say contact, we don't say field. We're choosing these to allow us to say, hey, and normal. Here are the forces that are acting upon it. Okay, we don't use contact, we don't use field. It's normal, friction, tension, applied, gravitational, magnetic, electrical, spring. It's another one. Okay, so you have to identify all the forces that are acting upon an object at any given time. All right, so steps to draw a free body diagram. Isolate the object. So biggest thing, what I do for every free body diagram, when I have to draw them or have to do them in some sort of way, I just make a box with a dot. You don't even have to put the dot in it. Just put a box, okay? And then you have to, step 2, identify all the forces that are acting upon that object. If this is something that's falling out of the sky, this would be force gravity, force air friction, right? And what do you notice about the force gravity arrow? Well, it's going down, A. What else? It's bigger, right? Why? Because gravity has a more of a magnitude than the air friction does, so the object is going to continue to fall. Okay, so even if you don't have any numbers to look at this, you can say, okay, I can see that this arrow is longer, force of gravity is longer than the arrow for air friction. So which way do you think that this object is moving? Downward. Good. All right. So you have to be very, very careful when you're drawing your arrows in these free body diagrams. Because if you don't draw them correctly, God bless you, Dallas, it's going to screw up your free body diagrams. Because say you decided that you want to draw this, and even though it is gravity moving down, but you just do FG and you do F air friction, which way does that look like it should be moving? It should be moving upwards. That's wrong, okay? Air friction is never going to override gravity, all right? So that's not the way it should be. So it should be FG, F air friction, okay? All right, so that's how we start to do this. So you use the arrows to represent the forces. The length of the arrow indicates the magnitude. The more magnitude something has, the longer or bigger the arrow should be. Okay, the direction of the arrow shows the direction of the force. Gravity, always pulling down. Air friction, always going against whatever way the object is moving. So, we have a book on a table. You have to identify what the forces are. Okay, so it's sitting on the table. So here we go. We're going to draw our little box. So here's our book. Okay, it's sitting on a table. So what's first? And it's not moving. So what's the first weight, or what's the first arrow that you're going to draw? Gravity going downward. Okay, so FG is going downward. What's the other arrow that you're going to draw? And what direction? Normal force, good. And normal force, which way? And how long should the arrow be?
The same.
It says shorter. You say the same. Why, Joe?
Because it's not going down.
It's not moving. So because it's not moving, it's going to be about the same. So this should be force normal. Okay? They're about the same. Okay? So that shows that there is, so this would tell you that there is zero net force. And what does zero net force tell you? That the force is balanced. Zero net force tells you it's a balanced force. Well, what do we know about making things move? What kind of force do you need? An unbalanced force to make something move. So in this case, the forces are balanced. There's zero net force. Everything's the same. The book's not moving. All right? Questions about that? Does that make sense? God bless, Dallas.
Thank you.
All right. So now we have a hanging object. Okay? All right. So we have an object that's hanging. So there it is hanging. Not moving. Again, not moving. What's the first one you're going to draw? Gravity. What's the second one you're going to draw? Nothing's pushing against it. What's holding it in place?
The rope.
Which is applying what kind of force? Thank you. It says it right there, like below.
I didn't know that.
Tension. It's got tension. The object's not moving. How long is the arrow for tension?
The same.
Same as gravity. Okay? So force, tension. About the same. It's not moving. It's not moving left to right at all, so there's no other forces that you need to identify. All right.
What if it was moving?
Hold on. Draw a free body diagram for a car that's accelerating forward. Identify your forces. Applied, friction, gravity, normal. Those are going to be the four. So what direction do each of these forces act? You would think after the first 3 times when I tried to draw without it up, I would put it up. All right, so here's the car. All right. Which way is gravity acting? Downward. So let's identify the forces. So identify the forces. Force of gravity going down. What else? Applied. What else? Going which way?
No, back.
What's back?
How is that going up?
Hold up. Yeah.
To the left. The force of friction. To the left. What works? What's the pair that goes with gravity?
Friction.
Starts with an N. Normal. Which way is normal? Upwards. Okay. Couple things. You know that gravity and normal are going to pair. Okay, so you know that's a pair, and you know this is a pair. Couple things. Is the car moving up or down? So what should those two arrows be? The same. They should be the same length. So force normal, force of gravity. Okay? So you know that you have arrows both going left and right, but it says the car is accelerating forward. Which arrow is going to be longer? The one going to the left, which is friction, or the one going to the right, which is forward and applied?
Right.
Why?
Because it's accelerating, it's moving forward.
Exactly, it's accelerating this way, so the force applied should be longer than the force of friction. So if you looked at that, which way is this object moving?
To the right.
To the right. Why? Because the longer arrow is pointing that way. The two arrows going up and down cancel each other out. Okay, because it's not moving up or down, it's just moving to the left, it's just moving to the right, it's moving forward. Okay, so therefore, because it's moving forward, the applied line is going to be longer than the friction line. Questions about that? Does it make sense so far? Yeah. Okay. So now we have a person standing on the ground. You got to identify the forces. How do they balance each other? All right. All it says, God bless. All it says is that there's a person standing on the ground, so there's no motion. So ID your forces. 4 times. You would think I'd get it eventually. So what are the forces? ID your forces. What do you got?
Weight.
Well, weight is also known as what? Gravity. Which way is gravity going?
Down.
Okay. And then normal, which way is that going? Okay. So draw your box. How are your arrows going to be? Even. Good. Force normal. Force gravity. It's a balanced forces, which means the net force equals 0 newtons. Okay, so it's balanced forces. They cancel each other out. There's nothing going left or right because it's just a person standing there. Okay, so force normal, force gravity, arrow's the same length, the net force is 0. Questions about that? Oh, God. So when we analyze the free body diagrams, force is always going to equal mass times acceleration. You want to be able to calculate the net force and acceleration and discuss how those forces interact and balance each other out. All right, so let's do a couple more practice problems. Let's see, let's go here, let's go here, let's go here. Drawing 3 body diagrams. All right. Not what I wanted. All right. So, number 1. No, let's not do number 1. Let's look at number 3. An egg is free falling from a nest in a tree. Neglect air resistance. Diagram the forces that act on the egg as it's falling. So we're going to draw the egg. There's your egg. What are the forces? So it's free falling out of the nest. What are the forces that are acting upon it? Okay. Force of gravity, which is pulling it down. What else? Anything? No, there is not. So to draw this, all you got to do, it's the force of gravity. Is it balanced or unbalanced? Why? Okay, good. It's an unbalanced force. Okay. So a flying squirrel is gliding from a tree to the ground at a constant velocity. Consider air resistance. Diagram the forces acting on the squirrel. All right, so gliding from a tree to the ground at constant velocity. Consider air resistance. All right, so what do you got? You got the forces are, what do you got? Okay. Just pulling down, right? What else?
Air resistance.
Air resistance, which is going which way, Dallas? What else? Normal is only when something is sitting on something. What else? Anything else? And it's moving at a what? So what's that tell you about the arrows? Sure. Positive?
That's the same.
Why are they the same?
Because
You were right, Sean. Why are they the same?
Because it's constant
Correct. The velocity is constant, it's not changing. So because it's already gliding and it's already started at a constant velocity, gravitation and air are going to be the same. Does that make sense? Okay. All right. So we could do one more. We could do a rightward force is applied to a book in order to move it with a rightward acceleration. Consider frictional forces. Neglect air resistance. Draw a free body diagram for this situation. So what's it going to look like? So, couple things. It's moving across the desk. So you got to draw your object. There's your object. What are your forces? So it's going to be applied, moving to the right. What else? Moving which way? What else? It's on a desk. Force of gravity is going to be going which way? Joe, what else? Good, because it's sitting on the desk. So normal is going upward. Okay. So it only says that it's moving to the right. So what does that tell you about normal and gravity? What should those arrows be?
The same.
The same. Okay. Force normal. Force gravity are the same. Okay. Friction's moving which way? To the left, right? But it's accelerating to the right. So what's that tell you about the applied arrow? It should be what? Longer, right?
Yeah.
So the force applied is longer. Is this a balanced or unbalanced force? Unbalanced force. God bless.
Thank you.
So it's an unbalanced force, the net of which is moving which way? Net force is moving which way? To the right or positive? Because it's moving to the right. Questions? Does it make sense? Okay.